Welcome to the new module pertaining to event trees, that is the quantitative risk analysis of any hazard or hazard process. Now, it is an extremely important aspect for any kind of safety analysis because it relatively deals with the quantitative analysis that what are the probability and what are the different consequences for any kind of hazard that may happen during the process area. So, let us have an overview about the event trees. In this particular module, we will discuss about the various definitions related to event tree. We will go for various steps or the procedures or the guidelines they are related to event tree analysis. We will discuss about the occurrence frequency of any incident. Then we will discuss the mean time between the shutdown, mean time between the runaway with the help of certain examples. So, let us have a look about the various definitions related to this event tree. So, when an accident or a process deviation, that is an event, sometimes it is referred as an event, occurs in a plant, the various safety systems, both mechanical, human, come into play to prevent the accident from propagating. Now, we must understand that whenever there is a chance of an accident or accident takes place, then there is some deviation of the process properties or the process scenarios, because your process is customized for the safe operation with the help of certain safety devices, etc. So, you need to look into these deviations, and these systems, these safety systems either fail or succeeds. So, whenever you have any kind of safety system, then either it may fail or sometimes it may succeed with respect to its objective. It is just like that you are having a pressure cooker, that is the pressurized vessel. It is equipped with two type of vents. One is the safety valve, another one is the safety vent. So, frequently you may experience that steam is coming out or issuing from the safety vent, and sometimes if anything fails or excessive pressure built up, then safety valve may rupture, and by this way it can release the excessive pressure whatever built in with respect to steam. So, in that particular case it succeeded, but if it fails, then there may be a chance that that pressure vessel or a pressure cooker may collapse. So, sometimes if it collapses, then definitely it will attack to the weaker point. So, that is why these safety systems, they have only two options, either they fail or succeed. Now, event trees, they are used to follow the potential course of events as the event moves through various safety systems. So, let us have a look of this particular figure. Here you are having an accident. Now, as a part of safety, this particular system may have alarms, so it may be actuated. There may be certain control devices to prevent the accident, so those control devices may fail or succeed. Then in case of accident, there may be certain manual involvement or the human factor which we have already discussed. So, manual control may fail and sometimes the human error may involve. So, one or all three may contribute towards an accident. So, the probability of success or failure of each safety intervention is used to determine the overall probability of each final outcome. That is extremely important. So, event tree analysis evaluates the potential accident outcome that might result following an equipment failure or a process upset known as initiating event. So, you must identify that initiating event. This may be in terms of this particular formula, that is control. You may have a different control things, C1, C2, C3 up to Cn, plus the probability of success of control. That means you need to calculate the probability of each and every aspect, that is P1, P2, P3 to Pn. That gives you the overall probability of that event control. So, in case of accident, you need to calculate the overall probability of those event in control. Now, this analysis is a forward thinking process. So, analyst usually begins with an initiating event, which we had discussed in the previous slide. They develop the possible sequences of events that describes the potential accident. The analysis, the sequence considering for both the successes and the failures of the safety functions as the accident progresses. Remember, we sometimes in a common fashion we used to analyze the process with respect to the safety. We rarely or seldom we discuss about the failure of those safety devices. So event tree analysis or event tree, the quantitative analysis augment all those aspects. So an event tree is used to determine the frequency of occurrence of the process shutdowns or any kind of runaway systems. Now there are certain guidelines they are attributed to this event tree analysis. Now we have enlisted all those guidelines in various slides. Now first guideline says that define the system or area of interest. So you need to specify, must have a clarity or clearly define the boundaries of the system or area for which event tree analysis will be performed. So you need to earmark that particular area. Then second aspect is that to identify an initiating event of interest, like sometimes the component failure. Sometimes it may happen that there is an increase in temperature or a pressure, because in past various accidents they took place just because of the temperature and pressure increment. There may be a chance of a release of any kind of hazardous substance. There may be a chance of involvement of any foreign component, that may be through raw material contamination or maybe due to the process outcome, maybe as a byproduct or a side product or a waste product. So based on this particular knowledge, you conduct a screening level risk assessment to identify the event of interest or categorize of event that the analysis will address. So you must be very focused about it. Now these categories may include such things like as grounding, collision, fire, explosion or toxic releases. So we have enlisted all those things because they are the outcome, like toxic release, fire, grounding, explosions, etc. So on the basis of this particular aspect, you identify the safety functions designed to mitigate the consequences of initiating event. You need to identify the lines of assurance and the physical phenomena. Now these lines of assurance include both engineered system and the human attention, because you cannot overlook the importance of this human action. Also identify the physical phenomena like ignition, some sort of meteorological conditions that will affect the outcome of initiating event. In past there are several incidents like where the meteorological conditions plays a vital role. Sometimes the atmosphere is heavy, sometimes the humidity is on the higher side, sometimes the wind direction may play a vital role. Suppose there is a toxic release, then if the wind direction is towards the populated area, then the consequences would be on the higher side compared to the wind direction towards the low populated area or rare area. So you need to identify all those physical phenomena. Then you need to construct the event tree. And on the basis of this, you describe the resulting accident event sequences. So there are certain points you need to remember, and those points are that event tree analysis is based on binary logic, in which an event either has or has not happened, or component has or has not failed. So there are only two options, either this work or will not work. So it is valuable in analyzing the consequences arising from a failure or undesired event. It is generally applicable for almost any type of risk assessment application, but used most effectively in model accident, where the multiple safeguards are used as a protective feature. Now there is one approach called inductive approach. In this approach, you need to specify or identify an initiating event and work forward towards the final result. This identifies how a failure can occur and what is the probability of the occurrence of that particular failure. So this particular aspect is important while calculating the consequences. So event trees, they are used to follow the potential course of event as the event moves through the various safety systems. The probability of success or failure of each safety intervention is used to determine the overall probability of each final outcome. Now let us have a look of this block diagram related to the event tree. You are having some initiating events, maybe based on different type of component identification, component 1, 2, 3 up to component n. Then simultaneously you are evaluation of assessment success and failure rate for each component. So based on this particular aspect you are analyzing this failure rate of each component. Then based on these two important information, there is a development of basic event tree diagram. Now it can be divided into three different aspects. One is that the development of sequential effect. This may lead to the pruning of event tree analysis diagram. And second thing is that assessment of conditional dependency. This is again attributed to the pruning of the event tree diagram. So based on this particular aspect, you can construct the final event tree analysis diagram, and on the basis of this diagram, you can go ahead with the consequence assessment. So let us have a look about the binary logic model based on two things. One is the control success, another one is the control failure. So each event can have only two outcome, these two, that is the success or failure. The chain propagates similarly until the initial event terminates. So if let us have look that if I is the initiating event, and let us see that xi is the consequential events where I is equal to 1, 2, 3, and x is the success, that is S, and failure F. So this is the initiating event, maybe success, failure. Then again this success may be attributed to S2, F2 based on all kind of aspects, and everywhere you can design these two steps: success, failure, success, failure, etc. So the first step, that is the identification of initiating event, like this. Then the second step is that identification of safety function designed to deal with the initiating event, this one. Then you go for construction of event tree, that is step 3. Then you classify the outcome, that is you describe the resulting event sequences. And next step is to estimate the conditional probability of each branch. Here you can have the conditional probability of each branch. Then you go for quantification of outcomes in the next step, and based on all these aspects you go for evaluation. So the first step, that is the identification of initiating event. This may be identified during the HAZOP as a potential event that could result in the adverse consequences. So usually this involves a major piece of operating equipment or processing step, that is a HAZOP or sometimes study notes. Now the system or equipment failure, human error, or the process upset. So one example is that loss of cooling water to an oxidation reactor. So you may have a different type of aspect in the initiating event, like strategy, risk, different type of control methodology. You may have the proper information related to that particular industry or the process, and these are the supporting events for to identify the initiating event. So you analyze these aspects with the help of HAZOP analysis step, like you must have a proper strategy, you go for analysis. If this is the risk, then you must have a plan, then the process, all information related to the process must be available. Based on the process, you go for the assessment, what are the control methodology based on the information available to with the various resources. Then you need to evaluate, perform the review, go for the analysis, and perform the strategy. So all these aspects are sometimes interlinked if you perform this kind of HAZOP analysis. Then you identify the safety functions. So from PID process flow sheet or a procedure, find what safety systems are in place and what their functions are. So here we have enlisted different P and ID symbols for various valves like bleeder valve, gate valve, BAL, etc. Now these can include the things such as automatic controllers, alarms, sensors, operator interventions, etc. So on you, the event tree right across the top of the page in the sequence of the safety interventions that logically occurs. So you give each safety interventions an alphabetic letter notation. Then the safety system that automatically respond to the initiating event. The alarm, usually sometimes we use the term alarm, usually alarm that alert the operator when the initiating event occurs and operator action designed to be performed in response to alarms are required by the procedures. So there are several barriers or containment methods, etc. Now these are the intended to limit the effect of that particular initiating event. So this is the inherent property of that event. So this is the example of event tree. Now we are having the sprinkler system. There is a methodology called the call to fire department, outcome and the consequences. You may have a fire, there may be chance that a sprinkler system may succeed or it may be chance of a failure. Now if it succeeds, then this is subdivided into two things like success or a failure. Now if it succeeds, then it's okay, no problem, but if it fails, then there may be a chance of partial damage. So this is the consequence 2 and this is 1. Now in case of failure, then the failure methodology will succeed, then there may be a chance of a partial damage, the consequence is 2. Now if it fail, then there may be chance of system destroyed. So the consequence is 3. So this is the outcome, this is the methodology and this is the process or initiating step. Now step 3 is the construction of event tree. So you enter the initiating event on the left hand side like this, then list the functional responses chronologically. Here you have enlisted all the functional responses, then decide whether or not the success failure of the function can or does affect the course of the event here, which we have enlisted. Now if answer is yes, the event tree is branched to distinguish between the success and failure of the function. Here we have the branched in success and failure in both the aspect. The horizontal lines, they are drawn between the function that applies. Here you have applied the horizontal lines. Vertical lines are drawn with each safety function that applies, like success upward, failure downward, and no effect, there would be no branch at all. Now indicate the result of event, that is circle, you may indicate with the acceptable result, the cross circle, that is unacceptable result, like this. So here again one example is given, that is explosion. The P is equal to 0.1, that is the probability of event to happen. Now in case of explosion, the start of fire, that is true because the probability is 0.8, and the start of fire, that is false, that means there is a failure, the probability is 0.2. Then start of fire, that means the success. Then the sprinkler system not functioning, that is sprinkler does not function, the probability is this one. Then sprinkler does not function, then this one. Then the fire alarm is not activated, the fire alarm is not activated, fire alarm is not activated, that is false. So success, failure, may be activated, may not be activated. Then if it is not activated, succeed, then the critical damage you analyze through this one, that is the outcome. Similarly, if it is not activated, that is the failure, then the major damage is like this. Similarly, sprinkler does not function, the fire alarm is not activated, this is the interlinked thing. So that is the success, then the damage is represented by this one. The fire alarm is not activated, then the damage is given by this one. Now this gives you the event end, that is then the minor damage. So here the Pi is equal to Pi if true, then Pi is equal to 1 minus Pi if the false. So net probability is given by this function. Now accidents, they do happen. So when accident or process deviation, that is an event, occurs in a plant, various safety system, both mechanical and human, come into play to prevent the accident from propagation. Now these safety systems either fail or succeed. So we must look into the occurrence frequency. So follow the process through which each step to calculate the frequency of each consequence occurring. Now typically there are three final results, maybe in terms of continuous operation, maybe the safe shutdown, or maybe the runaway or a failure. So you have to look into three different results. Now there is a concept of mean time between the shutdown. So you need to evaluate this one. The mean time between the shutdown, MTBS, is calculated from this formula. MTBS is equal to 1 upon summation occurrence of all kind of shutdowns. So the mean time between the runaway way or runaway reactions, the MTBR, is calculated by this one. MTBR is equal to 1 upon summation of occurrence of various runaways. Now let us have another example of loss of coolant to the reactor. Sometimes it's a usual practice, and it do occurs when we are having any exothermic reaction or exothermic process within the system. So you may have to go because of the catalytic requirement, or maybe because of the process requirement. Sometimes you may need to introduce the coolant so that the reaction temperature may be at the appropriate level. Now here this is a polymerization reaction. Here you are having the monomer feed. This is the cooling water coil. Here you are supplying the countercurrent cooling water, and here the cooling water which is at elevated temperature is coming out. You are having the temperature controller, usually sense and usually actuates when there is a need of cooling. So it may happen when you are not having the continuous cooling type of system. So if it is if the system reaction temperature goes beyond the acceptable limit, then this temperature controller activates and it sends to the cooling water so that the adequate supply of cooling water may inside the thing. Now this temperature controller is usually affected or usually gets sensed by this thermocouple. Now here there is a high temperature alarm. Sometimes if it fails, then this alarm will actuate and it sends or it gives an indication to the operator in question so that the remedial measure can be taken to avoid any kind of process damage. And sometimes it may happen because sometimes this thermocouple may have a faulty, this temperature controller may have the faulty things. So if there is a rise in the temperature, then this alarm will come into the picture. So if you see this particular figure, there are three different safety devices. One is the temperature controller, another one is this thermocouple, another one is the alarm. Apart from this, you are having the cooling water supply, and this cooling water supply is usually supported by these temperature controller sensors. Now next step is that you need to classify the outcomes. Now there are four safety interventions. One is that high temperature alarm. Sometimes the operator noticing the high temperature during the normal inspection, then operator re-establishes the coolant flow. Sometimes because of the failure of this things, so he or she re-established the cooling flow, and then operator performs the emergency shutdown of reactor. Then you may go ahead with the estimation of the conditional probability. Now assume the loss of coolant occurs once per year, that is the occurrence frequency is 1 in every year. Now alarm fails say 1% of time placed in demand, that is the failure rate of 0.1 failure per demand, then operator will notice high reactor temperature 3 out of 4 times, that is 0.25 failures per demand. The operator will successfully restart the coolant flow 3 out of 4 times, that is 0.25 failures per demand. Then operator successfully shut down the reactor 9 out of 10 times. So these are the probabilities. So 0.1 failure per demand. So you may construct the entire event with the help of this resulting event tree analysis. You are having the safety functions like high temperature alarm. Operator notices the high temperature, operator restarts the cooling, and operator shut down the reaction. So here you may notice that initiating event, that is the loss of cooling, one occurrence per year we have already noticed. Then based on this analysis 0.99 and 0.01, then go ahead the success, failure, then continue you go for this continue operation. Then there may be a chance of shutdown, runaway reaction, then this circle is crossed. Now if it is there, then the continuous operation, shutdown, runaway reaction. So you may construct by this way, in terms of result you may construct this event tree protocol, and then you perform the event tree analysis. Then we go for the quantification of outcome. Recall the previous formula. If we are having the shutdown, then we have to sum up these things. Summation, that is 0.2250 occurrence per year based on this particular protocols. And if there is a runaway, you can calculate this one, etc. So we are having the 3 conditions of runaway, 1, 2 and 3. So after summing up, it comes out to be 0.02500 occurrence per year. Now the event tree analysis shows that a dangerous runaway reaction will occur on an average of 0.25 times per year or once in every 40 years. This is very critical analysis. So this is considered too high for this type of installation. Now a possible solution of this inclusion of high temperature reactor shutdown system. This system would automatically shut down the reactor in the event that the reactor temperature exceeds a fixed value. Now the next step is the evaluation of the possible outcome. So the lettering is used to identify the each final outcome. For instance, ABDA, this indicates that after initiating event A occurs, the safety system B failed, that is a high temperature alarm. The safety system D failed, the operator was unable to restart the coolant, and the safety system E failed, that the operator was unable to successfully shut down the reactor, that is the extreme condition. So the advantage, let us have a discussion about the advantage. They are the structural progress and mathematical approach. It gives the quantitative analysis. This can be effectively performed on varying levels of design details. They permit the probability assessment. Once we are having the advantages, then obviously it comes with certain disadvantages. So the event tree analysis can only have one initiating event. Therefore, multiple ETAs will be required to evaluate the consequence of multiple initiating events. So it becomes extremely cumbersome. The partial success failures are not distinguishable. This is a serious disadvantage. They requires an analyst with some training and a practical experience. Now let us talk about the applications of this ETA. Now to identify the sequence of event that follows a given failure or error, as it could lead to a loss in system performance. The result of an event tree analysis are accident sequences or failure sequences. They are useful in analyzing the effect of safety system or emergency protocols or procedure on accident prevention and mitigation. They are used during the definition, design, modification or operation phase of a system. So they are having the very wide spectrum. Now used as a tool for demonstrating the efficiency of accident prevention and mitigation techniques. Now, although this event tree analysis is primarily used for the safety analysis, it can be quite useful for quality procedure analysis dealing with the corrective action procedure design and development. So, this analysis has a great potential to add in process control when special cases are detected using this SPC. Let us have a look about the quantitative and qualitative risk analysis, a comparative note. Now, in the quantitative and qualitative both risk analysis identify all the hazards applicable at workplace. However, the quantitative risk analysis says that you need to select a large set of scenario, whereas in qualitative risk analysis they require a small set of scenarios with the largest consequences. Whatever consequences are there, you need to study in a large domain. In quantitative risk analysis, they determine the expected frequency, or in some other words, the likelihood. Whereas in the qualitative risk analysis, they obtain some feel of the likelihood of these scenarios. That means sometimes you need to take a note of anticipatory things, so they look into account. This quantitative risk analysis, they determine the consequences of all those scenarios and they combine all these results. So, you need not to worry about the near misses, and they calculate the individual risk around the plant. Whereas the qualitative risk analysis, they determine the consequences of all these scenarios. In quantitative risk analysis, they draw the individual risk on a map and compare with the acceptance criteria based on different criteria which we discussed earlier. Whereas the qualitative risk analysis aspect, they draw the safety distances on a map. So, in case if you wish to have an anticipatory aspect, then definitely the qualitative risk analysis is fruitful. The aim of quantitative risk analysis is to classify the features, count them and construct the statistical models in an attempt to explain what is observed, that is the physical inference. Whereas the qualitative risk analysis says the aim is need to be complete in a detailed description. The quantitative risk analysis says the researchers must know clearly in advance what he or she is looking for, whereas the qualitative risk analysis says that researchers may know only rough aspect well in advance and obviously what he or she is looking for. The quantitative risk analysis is recommended during the later phase of any kind of a research project, whereas the qualitative risk analysis is recommended in earlier phase of any kind of research projects maybe. That is why it is said to be an anticipatory one. In quantitative risk analysis, all aspects of the study are carefully designed before you collect any data. Whereas in qualitative risk analysis, the design emerges as the study unfolds. Again, repeating the word anticipatory. In quantitative risk analysis, the researcher uses the tools such as the questionnaire or equipment to collect the various kind of numerical data, etc. Whereas in qualitative risk analysis, the researcher is itself a data gathering instrument. So, this particular point is again important. The last point is that usually in quantitative risk analysis, data is in the form of numbers and statistics, whereas in qualitative risk analysis, the data is usually in the form of either words, picture or different objects. Now, question being asked that is there any difference? So, one scientist says that there is neither a strictly deterministic nor a strictly probabilistic approach to risk analysis. Each probabilistic approach to risk analysis involves deterministic argument, such as a deterministic approach includes quantitative argument which decide how the likelihood of event is going to be addressed. A key distinction between the fault tree analysis and event tree analysis, fault tree we are going to discuss in next other module, is that in the latter, that is in event tree analysis, an initiating event is assumed to have occurred, whereas in fault tree analysis this initiating event is usually the event for which the probability of occurrence is determined. So, the initiating event may be the result of a particular system failure, or it may be caused by some external circumstances such as natural phenomena, etc. So, in this particular module, we have discussed about the event tree analysis. What are the different guidelines associated for event tree analysis? What is the impact of this event tree analysis in terms of qualitative and quantitative analysis in the process industry? So, you may, for further reading, you may have a look of these references which are enlisted over here. Thank you very much.